Hey everybody. So what we're going to talk about in this video is I'm called rotated systems here. And so here's the idea. Let's just think about coordinate systems in general, right? So you might see what looks like a mismatch of a couple coordinate systems here. But let's think about what they mean. When I create an XY coordinate system, what I do with that coordinate system, right? If I create a point, I can describe where that point is by telling you how far it is from the y-axis. This is our x coordinate. And then I can tell you how far it is from the y-axis. Sorry, the x-axis. This is our y coordinate, right? So that vertical distance is the y coordinate. Maybe I'll give this a naught just to be a particular point. So that's what we're doing. We're describing it, points, positions, relative to an origin and two axes that we establish, okay? But there's nothing that says I can't describe this point in terms of how far is it from this axis and how far is it from this axis. In this case, they share an origin. I don't even have to do that, but we're sticking with the same origin here. Right, and so I could describe this as what I've called x prime naught and y prime naught, right? It's the same idea. We're just, it's just like you and a friend facing slightly different directions. If you're looking at an object, they might think of it as 3 feet to the right and 4 feet forward, but to you, that's going to be a little bit different how you might describe that if you were using horizontally and vertically, okay? So these coordinates have the same meaning. Essentially, we have to abstract a little bit, right? So when we talk, let's go to the red coordinate system, our first coordinate system. The x coordinate tells us how far we've moved horizontally, okay? But another way I can think about that is how far have I moved in a perpendicular direction to the y-axis? That's what horizontal is in this case because the y-axis is vertical. And in the same way, the y coordinate is how far have we moved vertically from the horizontal axis, the x-axis, right? But again, we can think of that as how far have we moved perpendicularly, straight up from it. So if we look at the prime coordinate system, the one that I have in blue here, the meaning is the same. If I take the x coordinate, it's what is the perpendicular distance. The x prime coordinate is the perpendicular distance from that point to the y prime axis. And the y prime coordinate is the perpendicular distance from that point to the x prime axis. So we're still doing essentially the same thing. We've just turned a little bit, okay? And the idea is sometimes a particular coordinate system might be more convenient than another one, right? We can imagine situations like that all the time. For instance, when you picture yourself, most of us as we walk around the universe, we kind of have a moving coordinate system. We're the origin and we think of things in relation to us, right? So if we're navigating from home to work, as we make our decisions about how to turn, it's from our own origin system, ourselves as the origin of a system. And if we were sitting at work trying to navigate home, we wouldn't picture ourselves at home. And I don't know, it's kind of confusing to think about, but we don't picture ourselves from other coordinate systems. And so it's often convenient to choose a different coordinate system. So it was a whole bunch of preamble. What we're going to do is figure out a relationship between these two systems. In particular, let me clear some of this up without erasing anything I need. What we want to do, we're going to try to come up with a way that, given the XY system, we're going to convert to x prime, what I'll call the x prime y prime system. Okay. To do this, we're going to find two functions. Okay. So this notation is going to be a little bit strange. We're going to find two functions that relate Explain what all this means if you've never seen functions of more than one variable before. That the way these functions will work is that if they relate the x prime y prime coordinates and give us the x coordinate, right? It'll change. So you would need to know the coordinates in one system to get to the other system, right? So this is a function between them. So if this notation is a little bit confusing, we'll get there. You'll see what we mean in just a few minutes and how it works. Okay, so let's go ahead and work through this. And what we're going to use a little bit to do this, well, a few things. So we're going to use a little bit of the trig. We're going to use a little bit of trigonometry. So we're going to think about how these coordinate systems relate in terms of what angle they've been rotated through, right? So theta represents the angle of rotation you get from the first system xy to the x prime y prime system, right? So we're only thinking about systems that share an origin here, and the difference is a rotation. Okay, that's the first part. Now we're going to use a little bit of some of the notions. We're going to use vectors to do some of this. So suppose, right, my system x prime y prime, I can think of vectors in this system, and I can have unit vectors. Just like we have, pretend that's right along the y prime axis, just like we have unit vectors in our regular system, I and j, I hat and j hat, I can have vectors I hat prime and j hat prime, right? So it just means the vectors, the I hat vector, for instance, I hat prime vector is a vector in the direction of the positive x prime axis, 1 unit long, okay? And j hat is a vector 1 unit long in the direction, it looks funny, I feel like I should have that prime underneath the hat. That's bugging me for some reason. So this will be j prime hat, this will be, I don't know if there's an official way that works, but I don't like how that looks. Anyways, there's our 2 unit vectors in the direction of these new axes, okay? So let's look at I hat for a second. Let me redraw this over here. I'm gonna need space, so I'll draw it up here. So I've made it a little bigger. I don't know, I can't decide on which one to use, which way to write that. So here's our vector I hat, and this is the origin, and it points at some point right there. Here's the angle theta. In the old coordinate system, in the xy system, the distance this vector moved to the right would be the x coordinate, and the distance it moves up would be the y coordinate, right? It's a unit vector in both systems. Whichever way we look at it doesn't change how long it is, right? That would be what we would call invariant under rotation. It doesn't change, right? Rotating our perspective doesn't change how long something is. What we're talking about is how do we describe this thing, right? And in terms of, if I'm a person who lives a little bit rotated looking at the world, this vector I is just perfectly on my positive x prime axis. But in this other world where we are what we think of as horizontal, this thing's at an angle, right? The angle theta, and its x and y coordinates look to be both positive numbers versus maybe I should write this, in the original coordinate system, in the prime coordinate system, would just be 1, 0, because this 1 means 1 unit in the positive x prime direction and 0 units in the y prime direction. It doesn't tell us about the x and y directions because they're not the same direction as x prime and y prime. But we can use a little trigonometry here. All right, I can write that I prime, well, no, let's do something else first. Let's look at this distance right here. The distance here, we know that the cosine of this angle is going to be this distance that I've labeled x over 1, or just x. And the sine of theta is going to be y over 1, or just y. Okay? So if I want to write, I can write I hat prime in terms of unit vectors so here's I hat and j hat. I can write this vector in terms of these original unit vectors, right? These vectors live independently of how we choose to describe them. They're these geometric objects. And from this picture, it's pretty clear that if I take cosine of theta times I hat plus sine of theta times j hat, I get I prime hat, right? Because what is cosine theta I hat? Well, that takes this unit vector I hat in the positive x direction and scales it to cosine theta, which we just decided was this length. So that gives us a vector right here. It's not going to be unit length anymore. We've scaled it by cosine theta. And then we do the same thing to j hat. We add a vertical vector scaled by sine of theta. The addition of those two vectors gives us I hat prime. Okay? Let's do the same thing with j hat. So again, I'm just going to redraw that vector j prime hat. So this is j prime hat. Looks a little off, but the picture, I only need the picture to do this. So here's my angle theta. This is now my x direction. This is now my y direction. So again, let's use some trigonometry and see that cosine of theta is going to be y over 1, or y, right? So the y direction now is my adjacent angle. Sine of theta is a little bit different. Notice the x direction is negative, right? But when we're talking about these, the trig functions in relation to triangles, we're just talking about distances. So I need to make that, this negative x value positive by multiplying it by a negative. Okay? And so in the same way, we can say that j hat prime is going to be equal to, so the x direction, I'm going to do this one first. We're going to take negative, so I've written this as sine theta equals negative x. That's equivalent to saying that negative sine theta is equal to x. So the x coordinate that I want to move, the amount of distance I want to move in the x direction is negative sine theta. And I'll multiply that by my unit vector I hat. And then cosine theta times j hat. All right. And again, this is just taking my unit vectors in the xy system, scaling them to the appropriate lengths, and in this case, direction to get that negative in there. And we get these nice relationships. Okay, this tells me how to build unit vectors in the I prime, j prime, sorry, x prime, y prime system based on unit vectors in the xy system. Okay, we're still not where we want to be. We still haven't gotten to these functions, but we're getting there. Okay, we're going to keep using vectors for a minute. All right, now let's hold on to these for a second. We're going to come back to these. Let's consider a vector u, which is a vector I'm going to describe in the xy system X prime, Y prime system. What I mean by that is, first I'll write it and then I'll draw a little picture. Plus Y prime, J prime. Right. So all I'm saying is, remember, I'm going to keep making this point over and over and over again. Vectors are vectors, regardless of how we decide to describe them. So this vector U might be some vector like this. Okay. I could choose to describe it by how far does it go in this X direction and how far does it go in the Y direction, and give you those two coordinates to describe this vector, or write it as that distance in the X direction times I hat and the distance in the Y direction times J hat, and add those two vectors together, right? That's one thing that I could do. But I can also choose to describe it as some distance in the X prime direction and some distance in the Y prime direction, and then take unit vectors, right, and scale them and add them together. And this is what I've done here. X prime I hat prime would be this vector here, X prime I hat. I know this is getting messy, right? But that's a scaled version of our unit vector in the X prime direction. X prime here would be some negative number, it looks like, from the way I've drawn it. And then this vector down would be Y prime times J hat prime, right? A scaled version of the unit vector telling us how far to move. When we add them together, I get U. So that's all I've done here, okay? Now, I'm going to use these two relationships. X prime, I'm just replacing I hat prime with what I came up with up here. So I hat prime can be cosine theta times I hat plus sine theta J hat. And then we'll have Y prime times negative sine theta I hat plus cosine theta J hat. Okay, because those are the same vector. I've figured out a way to relate these vectors. So I'm just writing this another way. Okay. Now let's do a little bit of algebra. What I want to do now is get all the things with cosine of, or sorry, with I hat together. So if you look at this carefully, we're going to get an X prime times cosine theta I hat and a Y prime times negative sine theta I hat. So let's put those together. I'll get X prime cosine theta, whoops, it should be minus Y prime sine theta I hat, plus we'll do the same thing for J hat. There'll be a sine theta times X prime and a cosine theta times Y prime. So what did I just say? X prime, doesn't matter what order, I don't have to match my notes, plus Y prime cosine theta J hat. Okay. This is still the same vector. I haven't changed the vector. I'm just talking about it differently. Right? I'm representing it slightly differently. So what does this mean? Let's change notation here. Let's look at this first line. If I have a vector written as the sum of two unit vectors scaled by some numbers, I can write that in component form like this, right? This is what we mean by this. This is the X prime, Y prime system, right? When we write in components like this, what we're saying is move X prime units in the X prime direction and Y prime units in the Y prime direction, which is exactly what we said in this first line, okay? But now I also have a representation in the XY system, right? This first component, X prime cosine theta minus Y prime sine theta, and X prime sine theta plus Y prime cosine theta. This is in the XY system. Okay, so what does this mean? This is saying that if I want to draw this vector U, I can either move, as I've drawn here. Oh, I switched colors, sorry. As I've drawn here in red, this is a movement of x prime in this tilted horizontal direction, and then a movement y prime in this, what we'll call the tilted vertical direction. But I can also do this combination of things to get to the same point. Here I'm referencing directions in the xy system, right? So x prime is a number. If I take that number, multiply it by cosine theta, some angle, and then I subtract from that number the y prime number times sine of the angle, I'll get a number. That will tell me how far should I move in the x direction, not the x prime direction. And if I compute these values, because I'll know x prime, y prime, and theta, it'll tell me how far to move in the y direction, and I'll get the exact same vector, just described differently, right? So if you look carefully at these two triangles, this is a triangle that ends up, or if I think of it as two vectors added together, that ends up with this vector. So does this one. It's just a different, a different way to view the world. We're just tilted a little bit and describing things differently. Okay, we're really close. Okay, and here's the part that matters. If a little of this got a little bit messy in your head, here's where our result is. We can use this same idea to describe this point, right? The point that this vector is pointing at has the same coordinates in the x prime, y prime coordinate system. Its coordinates are just x prime, y prime. In the xy system, the coordinates are x prime cosine theta minus y prime sine theta, x prime sine theta plus y prime cosine theta. Okay, so this, again, this is in the x prime, y prime system. This is a representation in the xy system. Same point, same location, right? So me and you are standing in a room, or describing, let's say, a point that's 5 feet in front of me. I would say it has coordinates 0, 5. I'm going with x is to my left and right, y is forward and backwards, so 5 feet in front of me would be 0, 5. But if somebody else was standing this way, they might describe that as negative 5, 0. In the left direction to get to that point, so that would be the xy, would be negative, and no movement in that direction. Same point, just a different point of view, right? Just the way right and left change depending on which way you're facing, right? Two people facing the same intersection, one person on one side would say that building's to the right, the person facing them would say no, it's to the left. They're talking about the same thing, just describing it differently. That's what we have here, just describing it from a different point of view. So this gives us the functions we were looking for, because this is our x coordinate, this is our y coordinate. So here we go. Given, so we're considering an xy system, whoops, and an x prime, y prime system. Whoops. There we go. Created by a rotation through angle theta. Okay. Points in these two systems, or coordinates, are related by x equals x prime cosine theta minus y prime sine theta, and y equals x prime sine theta plus y prime cosine theta. Okay, so what this is saying to me is if I have these two systems laying on top of each other like this, where one system, the x prime, y prime system, is a rotation through some angle theta, if I have coordinates in the x prime, y prime system, and I want to write them in the xy system, I can plug the coordinates into these two equations and, knowing angle theta, come up with coordinates in the xy system. Okay, so for example, let's do one example of this and then a more complicated example. So for example, let's say I have let me copy those down. Let's bring these down with us. These are the big results that we're going to be using. Again, if some of what happened up above gets a bit messy, this is the result we need, how to relate these two systems. So if I have these two systems, so there's one coordinate system, x, y. Let's make actually, let's do it a little differently. Let's say my angle of rotation, let's see if I can get this right. It's close. I'm just going to leave it. I think I'll mess it up if I start drawing more. So let's suppose we know that this angle is pi over 6. Right? So if I have a point, so this is, sorry, I should have labeled this. This is going to be the x prime, y prime system. If I have a point that I'll put out, let's say about 3 units here and 1 unit, 2 units up. So this is, let's put it in blue for the x prime, y prime. The coordinates in the x prime, y prime system are 3, 2, meaning I move 3 units along the x prime axis and 2 units along the y prime axis. That's not how I would describe it in the xy system. So if I want to get the xy coordinates, I have x is equal to, well, x prime is 3, cosine, we know the angle is pi over 6, minus 2 sine of pi over 6. So what does this give us? Cosine of pi over 6 is root 3 over 2, so I have 3 root 3 over 2, minus sine of pi over 6 is 1/2, so I have minus 1, right? And then y is going to look like 3 sine of pi over 6 plus 2 cosine of pi over 6. So I'll get 3 times 1/2. Let's just write it as 3 halves. 3 halves plus root 3. 2 times root 3 over 2. Okay, so this point in the xy system has coordinates 3 root 3 over 2 minus 1 and 3 halves plus root 3. Okay, same point, same location, just how are we describing it, right? What do we, and you have to tell so many context. Here I'm using colors, right? So that I'm telling you that blue one is telling you how far to move in the x prime direction and how far to move in the y prime direction. The red one is telling you how far to move in the x direction and the y direction. If I don't tell you that, there's nothing distinguishable about these points if you don't have all that context. There's just a list of 2 numbers, okay? Okay, let's do one last thing. This is where it gets really interesting, probably. Let's consider this equation. What did I want? 2x squared minus xy plus 2y squared minus 30 equals 0. Okay. Now, you might recognize that this falls into the general form of what we call our conic sections, things like hyperbolas, parabolas, ellipses. Well, this turns out to be an ellipse, but let's take a look at it. Here's an ellipse but you can see that it's rotated, right? It's at an angle. Well, I can look at this ellipse from the perspective of different axes, right? So if you align your head now with those axes, if we think of, let's see, I need a pen. If I think of this as the x prime axis, and this is the y prime axis, these are axes that have rotated through by 45 degrees, okay? If we look at this ellipse from that perspective, I guess I should be turning this way. If we look at it from that perspective, this is not a slanted ellipse. And it's axes, it's you know, the distance between the two wide, or the line between the two widest points, and the line between the two I don't know, the other widest, the other widest direction, right? So this line from here to here and here to here lie right on this blue set of axes, these x prime, y prime axes, okay? And so if I could describe this instead of terms of x and y, right? This equation, 2x squared minus xy plus y squared minus 30, this is saying that if you put in points such that their coordinates are related by this equation, but here the coordinates are how far horizontally and vertically. If you put those points in this equation, they make it true, and that set of points is there. But we can, that set of points is the ellipse, right? The ones that satisfy this equation. But we could write that same set of points from the perspective of these prime axes. And from their perspectives, it's not tilted. And we talked about this in an earlier video. The big difference, at least a big difference, is this xy term, in the case of x prime, y prime, won't be there. So what we're going to do is use what we just learned to convert from one system to the other. Convert this equation. So here's how we're going to do that. So we're going to convert to system rotated 45 degrees. That was the amount of rotation I did there, right? Now, I don't expect you to be able to eyeball this. I knew this was set up to be this way. So we won't worry about how we know that at this point. Right now, we're just saying, if we know that we want to rotate by 45 degrees, how can we rewrite this in terms of that rotated system? Well, we're just going to use these equations again, right? So I'm just going to keep them here, ready to use. So how do we use them? Well, notice this equation gives me, so first let's just note, since we're going through sine of 45, we know that, sorry, rotation through an angle of 45 degrees, cosine of 45 degrees is root 2 over 2, or 1 over root 2. It's going to be a little simpler to use that, I think, right now. And sine of 45 is the same thing. Okay. Well, then that means x from the perspective of the x prime, y prime system is equivalent to the x prime coordinate times the cosine of 45. So that's 1 over root 2 minus the y prime coordinate times the sine of 45. So this is going to be x prime minus y prime over root 2. And y is going to be similar to something very similar. X prime 1 over root 2 plus y prime 1 over root 2. This is going to be equal to x prime minus plus y prime root 2. Okay. So I'm just going to take those expressions and put them into this equation. So my 2, let's just do it this way. So here's the expression, except in place of x, I'm just going to put what I just worked out there, x prime minus y prime over root 2. This will be x prime minus y prime over root 2. This will be x prime plus y prime over root 2. And this will be x prime plus y prime over root 2, right? So I just replaced all the x and y's into, replace them with this expression in x prime and y prime. All right, so let's do what we got to do. So what happens when we square this? We'll square the numerator and square the denominator. The denominator squared is 2. We've got a 2 up front. Those are going to go away, so we'll get rid of those. The numerator becomes x prime squared minus 2x prime y prime plus y prime squared. When we multiply these two together, we get root 2 times root 2 in the denominator. So that's going to be a 1/2. I'm just going to pull that out front. X prime minus y prime times x prime plus y prime. You might recognize this as the factoring of the difference of two squares. This is x prime squared minus y prime squared. And then at the end, we'll get exactly the same thing that we got at the front, except we have a plus instead of a minus. So this will look like x prime squared plus 2x prime y prime plus y prime squared. And I'm just going to add that negative 30 to the other side. So we have this. Okay, let's do a little bit of algebra. First of all, I've got a minus 2x prime y prime and a plus 2x prime y prime. I've got x prime squared minus half x prime squared. So adding those two together, I got 2x prime squares, take away half of one, I get 3/2 x prime squared. Let's look at y prime. So these are all taken care of. I've got a y prime squared, and then I'm going to have a minus 1/2 times a minus y prime. So I'm going to add 1. So 2 y prime squareds plus another half gives me 5/2 y prime squared. And this is still equal to 30. Let's divide everything by 30. Okay. What do I get? I have 1 over here. So when I divide this by 30, we'll end up with x prime squared over 20 plus this will be y prime squared over 12. This represents the same set of points that this equation does. The difference is these are points described by x prime and y prime. And notice how much simpler the equation is. This is our standard equation of an ellipse. There's not this weird middle term that we have to deal with because we've looked at it we're looking at it from a set of axes that are rotated to align with it, which is a simpler way to look at it. It might not seem like a huge deal right now, but as you get into more complicated ideas in mathematics, and you have to do things with this equation, working with something like this, right? If you're doing some calculus with this, for example, can be much simpler than working with something like this, okay? So, and at least right now we see that this is a simpler equation, right? And we could not get rid of this xy term in this coordinate system and describe the same set of points. Let's do one last thing. Let's graph. So Desmos doesn't let me graph from this other set of axes. I just graphed lines that look the way the axis does. But let's, instead of, we'll see what this looks like from the perspective of the rotation by putting that equation we just got into this. And now we see there is, so because of the limits in Desmos, I couldn't rotate the axes, but I've actually rotated the ellipse in the opposite direction, right? So it's as if we turned the whole thing to match those axes, right? But you can see how this shape now is a not cockeyed ellipse. It's I should have a better word for this. Aligned to the axes, I guess, is what I would say. Okay, that was a long one. I didn't think it would be quite so long. Thanks for hanging in there. That'll be it for this one. More to come. Thanks, everybody.